All right, welcome to day 4. Homework is packet page 46. And if you could be taking your warm-up sheet out, we're in a Thursday box for the warm-up sheet. So we want to find the 11th term of the sequence. So the first question we should always ask ourselves, are we dealing with arithmetic or geometric? I like to personally look for arithmetic first. So the sequence is clearly going down, and it's going down by 444. Well, if you go down by 444 again, that's not going to take you to 222. So that rules out arithmetic, meaning we're working with geometric. So we should be using the formula, an is equal to a1 times r to the n minus 1. You can get that right from your Regents reference sheet. Remember, it's good to put that r value in parentheses, even though it's not like that on your reference sheet. So we're going to find the 11th term. So the notation there would be A11. Our first term is 888. We'll talk about R in a second. And then for N, we'll have 11, so we'll have 11 minus 1 in the exponent. Remember, if you're not sure what R is, you can always do the second divided by the first. So here we can do 444 over 888, and that will reduce to a half. Well, now we've got everything we need. We can just type it in the calculator to see what we get. And it would give us 111 over 128. And that seems to make sense because we're getting smaller each time, so we should have something smaller than 222. And eventually, multiplying by a half, it's going to turn it into a fraction. So here's each of your homework ones. I'll pause on them for a second. If you have questions on them, you can post it in the content discussion board. And if you need it paused at any time, just pause it so you can check it, because I'll only stop for a second or two on each. All right, so our new stuff for today, we're going to be starting on packet page 16, and we're going to look at summations. So the summation symbol is the thing that kind of looks like an E. It's actually a sigma, the Greek letter sigma. And it means that you're going to add up or do a summation. So here's an example, the first example. What we always do is whatever the bottom number is, we sub that in for the variables in the expression. In this case, we only have k. So we would start out by subbing in 1 for k. And then it's a summation, so we add. So next we'll sub in the next number, which happens to be 2. And then we'll sub in the next number, 3. We'll stub in the next number, 4, and 5, 6. Oops. And how do we know when to stop? Well, the last number you should sub in is the number that is on top. So, 2 ways we can evaluate this now. We can type this all in. We could punch it all in all the way across. And it would give us 78. Now, we need to show this part where it's all adding up. But once we have that written, there is a shortcut way to evaluate it on the calculator. If you go to a calculator page, and the button that is just to the right of the 9, so that one that's in red, to the right of the 9, your summation template is in the second row. So right there. And then we can just type it in exactly as we see it. We've got k equals 1. That was our starting number. Our expression we had is k. and it's usually not going to be that nice. And on top we had 12. And if you hit enter, that gives you the 78 for you. So on the ones that you'll have in class today and on for homework, I'm okay if you actually evaluate it by doing that, but you need to at least show the work and show that you know what it's representing. So I need to see this addition written out, but then if you want to type the summation in your calculator, you can do that. So the second example, the first number we're subbing in here is 2. So we should have 2 being squared, then plus. Next number we'll sub in is 3, so 3 is squared, and then 4 is squared, and then 5 is squared, and the last one, the number on top, 6 is squared. So we would need to show that work, but then if we want, we can just go to our, oops, wrong one. We can just go to our summation key, so next to the 9, select your summation template. We started with j equals 2. We had j squared, and we stopped at 6. So if you hit enter, we get 90. So what that does is that automatically adds them all up for you. So moving on to the next one. Now notice our variables are changing each time, and they might do that. We can sub in the 1 first, so we'll have 2 over 1. Plus we'll sub in the 2 second, so 2 over 2. Plus 2 over 3, plus 2 over 4, and we finish with 2 over 5. We could use our summation to add that all up, and if we do that, we would get 137 over 30. And it's your choice if you want to type this in the calculator after you've got it written out, or type that. But I need to see that first row that you understand what the summation is doing. Going on to page 17, we're going to compare two different summations. 4x cubed, or 4 out in front of the summation, and then the summation of x cubed. So this one here, this first one, is we're going to sub in 1. Plus, we're going to sub in 2. Plus, we're going to sub in 3. Now the second one, we'll finish that up in a second, but I just want you to see the parallels. This is saying we're going to do 4 times, and then we're going to sub in our 1, 2, and 3. So we're going to have 1 cubed plus 2 cubed plus 3 cubed. And some of you might be able to see where this is going. But 1 cubed is 1, so this ends up as 4. 2 cubed is 8, so this ends up as 32. 3 cubed is 27, so that ends up as 108. This would be 4 times 1 plus 8 plus 27. So this would be 4 times 36, which is 144. And this one here would also give us 144. So notice they give us the same thing. And the reason they do that is, notice this 4 here, if it had been distributed, it would have matched what we had right there. So it doesn't matter if you have a constant, so a constant has no variables. If there's a constant that can be pulled out, you could put that in front of the summation and you'll get the same answer. And that's what's being shown in this rule here. A constant times some expression involving x's, that constant could be pulled out front and you could just do the summation of that. Now if you're doing this by hand, that makes it a lot easier. After we write it out, we're going to put it in the calculator, so it doesn't necessarily save us a ton of time. All right, so that's the easy way. The hard way is, what if they give us the summation and we have, or they give us the sum written out and we have to write the actual summation. So we've got 8, 11, 14, 17, 20, and 23. So we're going to start out with our summation, and it's usually easiest to start with n equals 1. Well, let's see, this is going to be the first, second, third, fourth, fifth, and sixth, so that would mean that has to be a 6 on top. Well, what we want to do next is notice the pattern. The pattern is going up by 3 each time. So think of that as like a slope, like a y equals mx plus b, where 3 would be our slope. Now, I chose n for the variable here. Just like we saw in the other examples, you could choose anything. We could have used x. We saw j on one, k. I just happened to pick n here. But let's see what happens here. If we sub in 1 right now, 3 times 1 will give us 3. That's not what we want. We want to get 8 back. So we need to think about what adjustment do we have to put on the end? Well, we would need to go up by 5. So 1 times 3 is 3, plus 5 is 8, so that checks out. Then next we would sub in 2. 3 times 2 is 6, plus 5 is 11. So now that is going to check out. So this would be one summation that would work. Now the question asks us to write 2 summations. So all we change with this is we can change the bottom value. And I would say always do n equals 1 or your variable equals 1 for the first one, and then either do 0 or 2 for the next one. So let's maybe do 0. Well, if this is the 0, then that's the 1, the 2, the 3, the 4, and the 5. So the top number changes when you change the bottom number. So we're still going up by 3, so that part's not going to change. But if we sub in 0 for n, 3 times 0 is 0. So now we got to think about what adjustment do we have to make on the end? Well, we need to be 8 higher. If we sub in the second number, which would be 1, 3 times 1 is 3, plus 8 is 11, and then that checks out. So those would be 2 summations. And there's really an infinite number of correct ones, because you could change that bottom number to be whatever you want. Similar idea on the bottom of page 18. We're going to do 2 summations. When you have a fraction, just treat the numerator and denominator separately. So we're going to do n equals 1. Well, this would be the 1, 2, the 3, and the 4. So 4 would go on top. So let's look at just our numerator and see what the pattern is. Going from 1 to 3 to 5 to 7, we're going up by 2 each time. So we would want to start with 2n. Well, when we sub in 1 for n, we would get back 2. What adjustment do we have to make to the 2 so we get the 1 that we want? We would need to subtract 1 on the end. Now check the next thing. When we sub in 2, 2 times 2 is 4, minus 1 is 3. All right, that looks like it's checked out. In the denominator, the pattern is also going up by 2 each time. But when you sub in 1, you get back 2, and we want it to be 3. So what we need to do is add 1 in this case. If we subbed in 2 in the denominator, 2 times 2 is 4, plus 1 is 5, and that looks like it's going to check out. So that's one summation. The next one, we'll change our bottom number. We changed it to 0 last time. Let's just show you an example of changing it to 2, because really you could change it to what you want and then just adjust. So this is the second, 3, 4, so top would have to be 5 now. Our pattern in the numerator is still going up by 2, so we'll have 2n. But now when we sub in 2 for n, 2 times 2 is 4, so the adjustment we would need is a minus 3 on the end. In the denominator, it's still going up by 2, so we have 2n. 2 times 2 is 4, but we need 3, so we would need to go down 1 then. And this would be an example of a second summation you could do. All right, if we go to the next page, we'll start with summation. 1 is easiest. 1, 2, 3, 4, 5. So 5 would go on top. Now the numerator, you're going up by 1, but then you're going up by 2, then you're going up by 4, and then you're going up by 8. So there's not a consistent pattern, so it's not going to be like a linear type thing in mx plus b. But in each case, the pattern is you're multiplying by 2 each time. So when you multiply by 2 each time, that's exponential. So exponential is something raised to a power. So what we'll do is we'll start with 2 raised to the n, and then we'll see what adjustment we have to make. Now your adjustment in exponential's general form is a times b to the variable. So we'll have to put some number out front possibly. When we sub in 1 for n, we get 2. So we need to think about what do you need to multiply 2 by to get back 1? And you'd have to multiply it by a half. If we sub in 2, 2 squared is 4, 4 times a half is 2. That's going to check out now. Now on the bottom, we've got to have a square root. Under our square root, we go 15, 11, 7, 3. We'll talk about the I eventually when we get there. But the square root, it's going down by 4 each time. So this one we can think of like an mx plus b. We'll have minus 4n. But if we sub in 1, we're going to get negative 4 in this spot, and we need it to be 15. Well, 15 is 19 higher, so we'll need a plus 19 on the end. Now let's think about where that I is coming from. If we followed the pattern, that last one should have a square root of negative 1 on the bottom. And square root of negative 1 is the same as saying our imaginary unit, I. Now for our other summation, maybe we'll go back to trying it with 0. So this would be 0, 1, 2, 3, and 4. Oops, I forgot to box in the n part of that. So on top, we're going to have 2 to the n still. It's just our adjustment that might change. Well, when you put in 0, you get back 2 to the 0, which is 1. When you put in 1, you get 2 to the first, which is 2. So we actually don't need any adjustment out front. You can put times 1 if you want, but that's not needed. In the denominator, our pattern is still minus 4. When you put in 0, you get back 0, and we want 15. So now our adjustment on the end is just a plus 15. So we're going to skip the bottom of page 19, and we're going to go to the top of page 20. Now on your homework, I'm going to want you to actually write out each thing that gets subbed in. But this is an example of why it's helpful to have that calculator button. In this example, we would have to sub in 6, and then plus. Then we would sub in 7, and then plus. And then we'd have to sub in 8. And we'd have to go all the way to 30. Well, that would be a lot of writing out. So that's why we have the calculator button for those really long summations. So we can just do our summation. We are using k in this case. We could have k equals 6 to 30, 2k minus 10. Hit enter, and it gives us 650. So that's the purpose of the calculator button. So when you have ones where it'd be way too much to write out. Now again, on your homework, I want to see at least that you've subbed them all in and show that they're adding them up, and then if you want to use the calculator button, if you can. If you want, you can. So we're going to show you, kind of model what I would want to see on your homework on these next two. So in the first one on the bottom of page 20, you got the 3 out front. So you can do 3 in parentheses. We're going to start by subbing 2 in. So we'll have 2 squared minus 5. And then plus, because of the summation, now we sub 3 in. So 3 squared minus 5. Plus, now we sub the 4 in. So 4 squared minus 5. Now from here you would have two options. You could type in exactly what you see, or if you wanted to type in the original summation, you could. Either one, it's your choice, and we would eventually get 42. But that's what I would want to see on the homework, is show that you understand what's happening with the summation by subbing in, but then after you've done that, if you want to type in the summation just on a calculator page, you can. All right, in the bottom of page 20, the last one, we're going to have -1 with the 1 subbed in over 2 times 1. Then we'll do plus. The next one we'll sub in is 2, so we'll have negative 1 to the 2 over 2 times 2 plus negative 1 to the 3 over 2 times 3 plus negative 1 to the 4 over 2 times 4. And I would say it's probably easier to just put in the original summation for this, but we would eventually get negative 7/24. Okay, so moving to page 21, we're going to only do the top of page 21. So these are the ones where we want to write the sigma notation, but what's nice about this one, we're only going to write one option. We're not going to do two different options. So let's start out, I guess we'll stick with n. So this is the first, second, third, fourth, fifth, so 5 would go on top. Now let's see what the pattern is. We're not adding the same thing over and over again, because you add 1, then 3, then 5, then 7. We're also not multiplying over and over again. So we need to think about what type of numbers are those? 0, 1, 4, 9, 16. What type of numbers are those? And the answer is they're perfect squares. So we're going to need to have something squared. Well, to get back 0, this is 0 squared, 1 squared, 2 squared, 3 squared, and 4 squared. But we're going to start out, we have 1. So if we just made this n, that would make the first thing be 1 squared, and we want it to be 0 squared. So what we would need is to take 1 away from it, n minus 1. Because then the second one would be 2 minus 1 is 1 squared. The third one would be 3 minus 1 is 2 squared, so then it would match up. In B, we'll have n equals 1. This is 1, 2, 3, and 4. On top, we're just going up by 1 each time. So you can either just write n or 1n. And notice by subbing in 1, it gives us what we want. Subbing in 2 will give us the correct thing in the second one. So you can do either 1n, or you can just call it n, because that's the same thing. On bottom, we're going up by 1 each time, so we can do n. But in this case, subbing in 1 gives us 1, and we want 2. So we have to go up 1 more, so we'll have n plus 1 on the bottom. Moving down to C, we'll have n equals 1. There's 1, 2, 3, 4, 5. So we'll have 5 on top. In the numerator, it looks like we'll have a square root for all of them. And if we look at those numbers, 1, 8, 27, 64, 125, there's nothing we're adding over and over again, and there's nothing we're multiplying over and over again. But those are a special type of number. Those are all our perfect cubes. 1 is really 1 cubed, 2 is 2 cubed is 8, 3 cubed is 27. And that matches with the number that we would put in. So this would just be n to the third under the square root. On the bottom, our pattern is we're going down 3 each time. So we'd have minus 3n. And if we check and see, subbing in 1 would give us negative 3. So we need to add something to get up to 14. It would be 3 to 0 and then 14 more. So we would need 17 altogether. And the last example, we'll start with our n equals 1. So 6 would go on top. Our pattern this time is we're multiplying by 2. So we need to think exponential, so like an a times b to the x, or to the n in this case. So we know we're going to have 2 to the n. 2 to the first is 2, and we want to get back 3. So we need to figure out what number should we put in front here, so that when we do 2 to the first, it gives us back 3. Well, this is the same as saying 2a equals 3. And if you divide by 2, you get either 3 halves or 1.5. So 3 halves times 2 to the n is what would work. If we check the second one, 2 squared is 4. 4 times 3 is 12. Divided by 2 is 6. So that does check out with that one. So you'll see things where you evaluate the summation and ones where you have to write the summation on your homework.